statements, I just want to let you know that Dr. Kip Thorne is known for other things besides doing a stellar job on Interstellar. So, thank you, President Evans, for your welcoming remarks for this year's academic lecture. And I wish to thank the members of the audience for coming to this evening's lecture. It is truly a privilege to introduce Professor Kip S. Thorne, the Feynman Professor of Theoretical Physics, California Institute of Technology Emeritus, and 2017 Physics Nobel Prize Laureate, for decisive contributions to the LIGO detector for observation of gravitational waves. Kip Thorne co-founded the LIGO project in 1983 together with Ray Weiss at MIT and Ronald Drever of Caltech. LIGO stands for Laser Interferometer Gravitational Wave Observatory. There are two paired LIGO detectors, with one of them being located reasonably nearby in Livingston, Louisiana, just 200 miles away from here. By the way, at LIGO Livingston, there are Science Saturdays on the third Saturday of each month, certainly worthy of a visit. Beginning with his graduate work in the early 60s at Princeton under John Archibald Wheeler, Dr. Thorne has been working on the problems involving the science of general relativity and gravitational waves in one way or another over the past 50 years. You can read about some of his work on the inside cover of the program that you have with you now. I will first say a few words about John Archibald Wheeler. He almost single-handedly revived interest in Einstein's general theory, or general relativity, after World War II. Professor Wheeler also had a wonderful way with words. He popularized the term black hole, for one, and he coined the terms quantum foam, neutron moderator, and wormhole. And Beaumont has connection to John Archibald Wheeler. His brother, Robert Wheeler, was a professor here at Lamar in the Department of Geology. After earning his PhD and pulling a one-year postdoc at Princeton, Kip Thorne returned to Caltech in 1966, where he had been an undergraduate earlier. He immediately established a group in general relativity. By the age of 30, he was a full professor, which I think is still the youngest on record for Caltech. In 1973, he published with Charles Misner and John Archibald Wheeler the influential book, Gravitation. And the book is simply known as MTW by the initials of the authors. In the intervening 45 years, it is still considered the most comprehensive work on general relativity, with the textbook educating over 2 generations of physicists, and weighing in at a hefty 1,300 pages, which I carry right here. 1,300, it is not just a good source for all things gravitation, but a significant source thereof. Okay, so I will quote from 2 of Kip Thorne's popular books. From his New York Times bestseller, The Science of Interstellar, which is the topic of tonight's lecture, he writes on page 151, and I quote, "I formulated LIGO's scientific mission, and I spent 2 decades working hard to make it a reality. And LIGO today is nearing maturity, with the first detection of gravitational waves expected this decade." He penned these lines in 2014. From another national bestseller, Black Holes and Time Warps, Einstein's Outrageous Legacy, on page 50 of the prologue, Kip Thorne imagines 2 black holes swirling in and coalescing and emerging. Gravitational waves are produced. In his words, again I quote, "By measuring the starship's orbit, Keras deduces that the whole weighs 45 solar masses. Since the parent holes total 48 solar masses, 3 solar masses must have been converted into pure energy and carried off by the gravitational waves. No wonder you shook so hard." This was written in 1994. Now, let's move on to 2015, 1 year after the movie Interstellar came out. Success came on September 14th, 2015, when LIGO measured gravitational waves resulting from 2 massive black holes that spiraled in and merged into one gigantic black hole, 1.3 billion years ago. The original black holes were both around 30 solar masses. In the process, it dumped 3 solar masses into gravitational waves, making the event 50 times more energetic than the rest of the universe combined, for that one brief moment in time. The results were announced in February 2016, and the Nobel Prize came in 2017. LIGO is ushering in a new age of astronomy, an invention that ranks with the telescope. In the intervening 2 years, further black hole collisions have been detected, and on August 17, 2017, gravitational waves from the merger of two neutron stars were detected. This event could also be seen in the optical as a gamma ray burst, marking the first time that optical telescopes and gravitational wave observatories could work in concert. The event could be seen and heard. We are living in wondrous times. But my question to Professor Thorne is this. How did you guess back in 1994 that the first direct detection of gravitational waves could be from two black holes, each being around 30 solar masses, give or take, and dumping the energy of 3 solar masses into gravitational waves? This is exactly the event first seen at LIGO in 2015. Amazing. And with this introduction, let's please welcome Dr. Kip Thorne to Lamar University and to Beaumont, Texas.
Thank you for that overly kind introduction. I will return to gravitational waves at the end of my lecture, but for almost all of my lecture, I want to be talking about the movie Interstellar and how general relativity is embedded in that movie. So let me begin with the genesis of the movie. Interstellar is the product of a failed romance. September 1980, Carl Sagan, who was a close personal friend of mine, an astrophysicist, the creator of the Cosmos series of TV shows, the creator of the movie Contact, he set me up on a blind date with a budding young movie producer named Linda Oakes, who had previously been a science editor for the New York Times Magazine, had just been dragged out kicking and screaming by her husband, who wanted to move to Hollywood. It led to a divorce. But it also led to this blind date between me and Linda. Our romance didn't go very far, very fast. I was a bit too nerdy for her. She was quite a bit too intense for me. You know, I was a laid-back guy, as you can imagine. So anyway, we nevertheless became rather good friends. Fast forward 25 years, October 2005, Linda called me up and she said, would you like to brainstorm with me for a movie based on the science that you have been doing during your career? I thought about it for a few milliseconds. Responded yes. I thought to myself, this will be fun, but in addition, I could use this to inspire young people about science in the way that George Gamow, in a book called 1, 2, 3 Infinity, in a previous generation, had inspired me and gotten me into science. And indeed, that is what happened. The movie Interstellar sold about 100 million tickets worldwide. And how else can a Caltech professor inspire 100 million people except through a Hollywood blockbuster? So that, for me, was a big part of the motivation. So what we did is we wrote something called a treatment for the movie Interstellar. This is a description of a story, and in our case, but not in anybody else's treatments, except maybe going back to 2001: A Space Odyssey, decades earlier. In our case, it was the science embedded in the story from the outset. And it was general relativity that was embedded in the movie's fabric. It was the subject that I had worked on during my career. January 20, 2007, Linda brought on board Jonathan, or Jonah, as he's known to his friends, Nolan, to write the screenplay. Jonah had very little experience in Hollywood up until then. He had co-authored several screenplays with his brother, Christopher Nolan, who was not at that time involved in this movie at all. And that was it. Since then, he has gone on to create the TV series Person of Interest, and the series currently running Westworld. So he's now becoming a bigger name in Hollywood. He wasn't particularly big at that time. He spent about 3 months reading relevant science books that I fed to him, getting his feet under himself in the science of this movie. And then he brainstormed with me on the science through 3 drafts of the screenplay. We would get together for a 3-hour lunch at the Caltech Faculty Club every few weeks while he was working on the screenplay to discuss ideas that were going into the movie and go back and forth with these ideas, saying how to incorporate them, how to understand them, how to make them understandable to a general audience, and embed these new ideas as they were coming to us deep into the movie. December 2012, Linda brought on board Christopher Nolan, Jonah's brother, to write the final drafts of the screenplay and to direct the movie. And Emma Thomas, Chris's wife, who always is the lead producer on his movies, then came on board as well. I offered to Chris my proposal for the guidelines with regard to the science that I would like to see in this movie. I propose that nothing in the film will violate firmly established laws of physics or our firmly established knowledge of the universe. And the speculations about poorly understood physical laws and the universe will arise purely from real science, not from the pure thought of a screenwriter. And Chris's response to these proposed guidelines was, yes, I'm enthusiastic, as long as they don't get in the way of making a great movie. And then in the next breath he said, but if you don't like what I do with the science, you don't have to defend me in public. Well, needless to say, I felt just slightly uneasy. I was encouraged he didn't want me to defend him in public when he mutilated the science, but just a bit uneasy. But he was even more uneasy. He was afraid that I would play the role of what he later called to me the science police. And I would tell him what he could do and what he couldn't do. Now, his brother, John, with whom I had worked closely on the early drafts of the screenplay, kept telling him that, in fact, that's not the way Kip will operate. He'll brainstorm with you, and that is what we did. And in fact, after a few sessions, we found ourselves working together very easily and enjoying it enormously. So he brainstormed with me through 3 more drafts of the screenplay, and by the time he was done, and Jonah was done, the final screenplay and movie, although they preserved Linda's and my science vision, and they added a lot of new science that was really quite exciting that came from our brainstorming. They, on the other hand, changed the story and the characters almost completely. In a very crude sense, the final movie was our original story, but only in the crudest of sense. And so as a result, in fact, Interstellar is the Nolan's movie. It's not ours, not Linda's and mine. But in fact, the science is our science augmented by brainstorm new science from the Nolan brothers. In May 2013, Chris called me up and he said, I'm going to send over a guy to your house to talk about the visual effects in the movie. I said, sure, send him along. And so this guy came over. His name was Paul Franklin. And we talked for a while. It was obvious he was pretty knowledgeable. And so I asked him, what computer graphics house are you planning to use in this movie? And he said, mine. I had to look him up on the web before, so stupidly. So I said, what is that? He said, well, it is called Double Negative, and we have 1,000 employees in London and 200 in Singapore, and we will use a large fraction of them on this movie. Well, I was a bit ashamed that I hadn't looked him up previously. When I did go to look him up, I discovered that he had won the Academy Award for visual effects in the movie Inception. And later he went on to win the Academy Award for the visual effects in Interstellar. And so I just had a fabulous time working with him. Now I've told you about some of the people that I worked with on the movie. I'm going to let them tell you about me.
We are still pioneers. We've barely begun. Our greatest accomplishments cannot be behind us, because our destiny lies above us.
The initial impetus for the project being to say, why not examine real possibilities? Why not actually look at the real science there?
Luckily, we had Kip, and Kip is the foremost authority on all things gravitational.
The warping of space inside here scatters some of it back, glides scattering off of the surface of the rippled ocean. Neither wormholes nor black holes have been depicted in any Hollywood movie in the way that they actually would appear. This is the first time the depiction began with Einstein's general relativity equations.
The visual effects department under Paul Franklin and everybody at Double Negative took Kip's mathematical data and they created real visual representations of what a black hole is meant to look like.
The collaboration has produced visualization of things which nobody had ever managed to do.
So I cut him off there before he quite finished because the next thing is a whole bunch of equations up on the screen. I didn't think you really wanted to look at those. But in fact, what we did was we found that by the standard techniques that are used in order to, in making visualizations on the screen of something that's computed mathematically, which is tracing of light rays going from some source of light to the camera, that didn't give us adequate resolution on an IMAX screen when you're doing this around a black hole. So we had to invent an entirely new way of converting the results of computer simulations into visual effects. And we actually wrote a 40-page technical paper that is now used as underpinning for current and future visualizations of things around black holes, both in Hollywood and by astrophysicists. So it was a lot of fun working with the double negative team on this movie, and some really interesting technical techniques and science came out of it. The venue in which this movie occurs is the fifth dimension. Now what I mean by this is that in everyday life we have three space dimensions, north, south, east, west, and up, down. And then we have one time dimension. In order to tell your friend where you want to meet them, you have to say not only where in space, but also at what time. In that sense, time is the fourth dimension. In the movie, there is one more space dimension. So there are four space dimensions, but it's called the fifth dimension in the movie because time is the fourth dimension. And so the first three and the fifth one are space dimensions. In this talk, I'm going to use a technique of suppressing one space dimension so that I can depict the out-back dimension that takes you out of our universe up into what we call the bulk, the fifth dimension. And so you see here what looks like a plane with north, south, east, west, but I have removed the up-down dimension. And instead I'm showing now the fifth dimension out back, going out of our universe. And our universe looks like a plane instead of like a three-dimensional surface. Also, in this talk, as in the book that I ultimately wrote about the science of the movie, called The Science of Interstellar, I'm going to label, let me go back and say, the key thing about this movie is that about half of the science is science that we understand very thoroughly and we know it's true. And about half of the movie deals with science that we aren't completely sure what the laws of physics are. These are particularly things that involve the fifth dimension or involve what's called quantum gravity. And so we speculate in the movie about what those laws of physics are in those areas where physicists are not absolutely sure. And I'll return to some aspects of that speculation later. When I have an S up here, that means that this is speculation, not truth. When I have a T up there, it means it's truth. And so the fifth dimension is speculation. When I was a child, we had an apple tree behind our house. And the apples, almost all of them had wormholes in them. My father was a soil chemist, and he did not believe in using DDT on apples that we were going to eat. And so we had wormholes, and ants like to crawl through the wormholes. And if you think of an ant who lives on the surface of this apple, the surface of the apple may be the ant's entire universe. It can walk around and around on the surface. But the ant can also get out of the universe and go down into the interior. That's a higher dimension, and through the wormhole to get to the other side. So there's a long way around and there's a short way around. The short way around goes out of that surface dimension through the third dimension, which is the bulk. It's the higher dimension so far as the ant is concerned. Similarly, in Interstellar, we have, in that case, a three-dimensional universe, our brain it is sometimes called, which is embedded in that fifth dimension, the bulk. And you can imagine that perhaps our universe is bent around in the bulk. We wouldn't know about that if we live inside the universe. We wouldn't know it's bent around, but perhaps it's bent around like that, so that across the bulk, the distance between our solar system and some distant galaxy is only a few kilometers, whereas through the external universe, it may be 10 billion light years. And in the movie, there is a wormhole that reaches through the bulk, like the wormhole that reaches through the interior of the apple. This wormhole is something by which we can go from the vicinity of Saturn down the surface of that wormhole. Remember, I've suppressed one spatial dimension, and so you think of us as being like two-dimensional beings who live on the surfaces, not in the interiors. The interior is the bulk. So you can go down the surface of this wormhole to get from our solar system into that distant galaxy. Now, in the making of the movie, Eugenie von Tunzelmann, a superb artist, she led a team of about 100 artists who made paintings of what goes on in that distant universe. I worked out equations for the propagation of light beams from the distant galaxy up through the wormhole to an IMAX camera in the vicinity of Saturn. And Oliver James programmed a big supercomputer to solve those equations numerically, to thereby produce an image of what the camera would see looking through the wormhole at that distant galaxy produced by Eugenie and her team of artists. So here is a picture that they produced. Saturn looks about the same size as the wormhole, but that's only because the wormhole is very close to us. The wormhole actually has a distance across it of a few kilometers, whereas Saturn is much bigger than the Earth, but Saturn is much farther away, so it looks about the same size as the wormhole. I'm now going to show you the trip through this wormhole as computed by solving Einstein's equations as I developed those equations, formulated them, and fed them to Oliver James. And this is the trip that Oliver James and his team actually produced. And this is what it would truly look like to travel through this wormhole from the vicinity of Saturn into the distant galaxy. Okay, we are moving closer and closer to the wormhole, and so Saturn is appearing to get bigger and bigger. And we enter the wormhole, we travel through the wormhole, we are now out the other side, and wasn't that an exciting trip? So, Christopher Nolan had just finished doing all the filming and was beginning to integrate the computer graphics into the movie. This was now around January or February of 2014. The movie was going to be released in November of 2014, so we were not that far away. He called me up and said, "Kip, we've got a problem. Would you come over to my house and let's talk about it?" So he showed me several film clips of this sort. He said, "This is what it looks like to go through the wormhole according to your equations. But this is never going to do for an audience of 100 million people around the world. What are we going to do about it?" And I sat there and I said, "Well, you're going to have to use artistic license." So I gave him the license to depart from from the actual prediction of the equations. So he went in and combined the predictions from trips through wormholes of several different sizes and shapes, and put on some music, and this is what you get. And if you watch this, you come to a point where Matthew McConaughey, playing Cooper, he pushes the joystick to enter the wormhole. Everything before he pushes the joystick is precisely what the equations say you should see. He should see, or the camera should see if it's sitting inside the spaceship together with Matthew McConaughey, Cooper. Everything after he pushes the joystick has artistic license. Okay, so let's watch. The movie's Trip to the Wormhole. So that's precisely what it would look like. about toward the end of the lecture. But if you want to know where the places were that Christopher Nolan deviated from the science, from the real science, all of them that I knew about at the time I wrote the book, I identified several more later on. All you have to do is go into the index at the back, look up in the subject index, look for the name of a person. Normally you don't do that. You look for Christopher Nolan in the subject index, and under Christopher Nolan you'll find an entry, all the compromises he made with the science in order to make a great movie. And there's a whole list of all the pages where you find those discussed. These were the things that he did, as I say, because he wanted to make a great movie. This is the only major one. Everything else is really quite minor. And I was tremendously pleased with the movie at the end, with how closely it did follow the science and how successfully it did. Do wormholes really exist in our universe? Probably not. The fundamental problem is that a wormhole is, according to calculations with Einstein's relativity, unstable in the sense that if you had a wormhole to travel through, gravity would grab hold of it on the exterior sides, and it would pinch off, just squeeze down so rapidly that you would get killed when you try to travel through it. Now, we do know that in principle, you can prevent that from happening if you thread through the wormhole a particular kind of material called exotic material. That's my name for it. The physicists really say material that violates the average weak energy condition, but I don't want to say that for an audience like this. So if you thread it with exotic material, then you may be able to hold the wormhole open. But the issue then is whether the laws of physics allow you to have enough exotic material to actually hold it open wide enough for a human being to go through. I and this number of colleagues of mine worked hard on this question, manipulating the mathematics of Einstein's relativity theory for several years, and we could not find the answer. We just weren't clever enough in solving the equation. So it's an open question whether wormholes really are a speculation or whether they actually can exist in the real universe. I am strongly convinced that if they are allowed by the laws of physics, they don't occur naturally. They'll only occur if some very advanced civilization builds one and puts it out there, which is what happens in the movie Interstellar. Interstellar travel is unbelievably hard by conventional means, and so in the movie we use wormholes, and we're justified because we've not been able to prove it's impossible. Black holes, by contrast, do exist in the universe. We have a lot of examples of them observationally. Black holes are truth, so a big T up here on the right. As seen from the bulk, a black hole looks like a failed wormhole. It comes down here and then does not open back up to join onto this other sheet of our universe, of our brain. The point that it comes to is called a singularity, though it's not really a point, as I'll explain in a few minutes. Interstellar's black hole looks like this. So the question is, how could it possibly look like that? It's so very different from what the wormhole looks like. And I'll explain why. This has become sort of the iconic image of a black hole that you see on the internet. The black hole is called Gargantua, and Gargantua has this kind of a form because there is what we call an accretion disk around it, much like the rings of Saturn, a disk of hot gas orbiting around and around in the equatorial plane of the black hole. And the camera in Interstellar is just a little bit above the plane of the disk. And so the gravity, the curvature, the warping of space and time pulls on a light ray that comes off the upper face of the disk and bends it around and down to the camera in that way. So the camera thinks the upper back face of the disk is up here. And that's what gives rise to the upper part of the image of this black hole. Similarly, a light ray coming off the bottom back face of the disk swings around the black hole due to gravity, warped space-time, comes up to the camera from that direction, so the camera thinks that the bottom back face of the disk is down here. That explains the bottom ring around the black hole. And then a light ray from the front of the disk goes up to the camera just straightforwardly and produces this crossbar. So a very simple explanation, but nevertheless it was quite startling to see this image come out of the equations when Oliver James, my colleague, did the computation based on the equations I gave him, this is what came out. Now, another piece of science that's quite interesting in the movie Interstellar is Einstein's law of time warps. And this is a law that says things like to live where they will age the most slowly. Isn't that where you would like to live? And gravity pulls them there. This law has a precise mathematical statement I'm not going to go into, but as an example of it, the Earth's mass warps time, and this time warp produces the gravity that holds you in your seat. Now that is a real weird statement of where gravity comes from, and that's nothing like what Newton said was the source of gravity. This is what Einstein says. And this was first tested in 1976 to enormous precision, 1 part in 10,000, 0.01% precision. When NASA flew atomic clocks built by a guy named Robert Vassaux, who was at the Harvard Smithsonian Observatory in Boston, flew atomic clocks up to a height of 10,000 kilometers and telemetered the ticking rate of those clocks down to the Kennedy Space Center and compared that with the ticking rates of Bob Vassaux's clocks that were down at the Kennedy Space Center. And that comparison showed, in fact, the prediction of how strong this slowing of time was agreed with the observations, as I say, to a part in 10,000. How did we make the prediction? We know how strong gravity is on the Earth. And you just had to go into Einstein's formulas and say how much slowing of time is required in order to produce the gravity that we measure. And that's what gave us the prediction, and it was a remarkably accurate prediction. Now, near a black hole such as Gargantua, gravity is enormously stronger, so the slowing of time is enormously greater. In fact, there is a planet, the water planet is sometimes known as, or Miller's planet, that is orbiting around the black hole Gargantua, quite close to the horizon of the black hole. And in the movie, 1 hour on Miller's planet is 7 years back on Earth, which is really quite startling, that enormous slowing of time down near the black hole on Miller's planet, 1 hour compared to 7 years on Earth. In the movie, before Cooper, played by Matthew McConaughey, goes out on his trip through a wormhole to the vicinity of the black hole Gargantua, he tells his daughter, his 11-year-old daughter, Murph, who's played by Mackenzie Foy, he says, I'm going to go out through this wormhole, and I might go near a black hole, and if I do, time for me will slow down so much that it may be that when I come back out, you have grown up and are as old as I am now. And that's precisely what happens. He goes down near Gargantua for a few hours, comes back, and Mackenzie Foy has been transformed into Jessica Chastain. She has grown up to be a theoretical physicist who is working hard to try to understand what's going on around black holes. McConaughey, or Cooper, has aged hardly at all. Cooper goes down near the black hole once again and comes back, and his daughter is now an old woman played by Ellen Bernstein. And it's a very emotional scene when he goes back and he meets with her. Again, he's aged hardly at all, and his daughter is now very near death. For a general audience, this is quite an emotional experience, and you get a real sense of how weird time can be that results, in fact, from Einstein's law of time warps. Another piece of physics that's really quite interesting and important in the movie is gravitational anomalies. That is, a gravitational anomaly is some behavior of gravity that is not in accord with our understanding of how gravity ought to behave, not in accord with anything we've ever seen before. And a beautiful example of this is when there has been a dust storm, and the dust has gotten inside the farmhouse where Cooper and his children live. And it has settled down, filtered down onto the floor, but it didn't filter down and fall onto a uniform sheet of dust on the floor. It fell into strips that looked sort of like long mountain ranges, strips of dust with no dust in between. And Cooper is sitting there staring at the strips when his daughter comes in, And he says to his daughter, he says, look, I'm going to toss this coin and see what happens. And every time he tosses it, it lands on one of these strips. It never lands in between the strips. It always lands on one of the strips. He says to his daughter, it's gravity. Gravity is not behaving like it ought to behave. It always falls on the strip, and the dust always fell on those strips. Something is wrong about gravity. When Murph grows up and goes to work with Professor Brand, he and she struggle to understand these gravitational anomalies. Let me just say as a side remark, Professor Brand is played by Michael Caine. I was on set when they were filming the scenes depicted in these movies, and the first assistant director who was in charge of the shoot came up to me and whispered in my ear. He said, Michael Caine would like to have his photograph taken with you. Is that all right? My jaw dropped. And I sort of stammered, well, yeah, yes, that's okay. So the photograph was taken, and then about an hour later, Michael Caine's wife came in and sat down beside me and whispered in my ear. She said, Michael said that you were on set, I should come meet you. And I asked her, why? And she responded, because Christopher Nolan, told Michael that his character is patterned after you. Now, Chris never told me that, but when you watch the movie, supposedly, Michael Caine is playing some variant of me. Also, with regard to this, Murphy Cooper, played here in her 20s by Jessica Chastain. Jessica, at the world premiere in Los Angeles, on the red carpet, she talked about only one thing: how wonderful it was to play the role of a theoretical physicist and to work with me and with Elena Merchikova, a Caltech graduate student, on the science of her role in the movie. The people involved in this movie, everybody, the actors, the studio executives, the director, the screenwriter, producers, they were all so enthusiastic to do a movie involving real science. It became a matter of great pride for everybody. And that was really tremendously gratifying for me. And so a mutual joy came out of all of it. Okay, let me return to this. Why were they struggling to understand the anomalies? In order to save humanity from a dying Earth, and you have to watch the movie again to remember how the Earth is dying. And they want to save humanity by turning off the Earth's gravity temporarily so that giant space colonies in big cylindrical structures can be lifted off of the Earth with very little rocket power, because they didn't have much rocket power, to bring off what remains of humanity, which is only a few 100,000 or maybe 1 million people on the entire Earth, because the Earth is getting into such bad shape. So to save them by lifting them off. So turn off gravity temporarily and then turn it back on once these space colonies are up in space. Now this is really wild. But it was my idea. And it came out of real physics, but speculative physics. You see the S up here, speculative physics. And so if you want to know what is behind this, in Professor Brand's office, there are 12 blackboards. And they appear in this piece of the movie that's filmed in Professor Brand's office. And all the mathematics that underlies what's going on with the gravitational anomalies is on those blackboards. Of course, you need to get a PhD in physics in order to fully understand this. But this is only Professor Brand's and Murph Cooper's speculation as to what's going on. They are not absolutely sure. And Murph says, we have half the answer here. We've worked out half the answer. It's now on the blackboards. The other half is inside a black hole gargantua. And the only way we're going to get that other half of the information is by going down inside gargantua and observing what goes on inside the black hole. Those observations will tell us about the laws of physics which govern this singularity inside the black hole, which I'll return to momentarily. Those laws of physics are the laws of quantum gravity, but in this case in 5 dimensions. And if we can understand those through observations near the singularity, then we can put the pieces together and really know how gravitational anomalies work, and we can harness those gravitational anomalies, we hope, in order to turn off gravity temporarily to lift humanity up into space. So it's pretty wild, but it really is based on speculative versions of the laws of physics. So Cooper plunges into Gargantua with the goal of finding out about the laws of
Mine doesn't count. Approaching the event horizon. Port side, dipping down beneath it. We go through it.
So this is quite interesting. If you listen carefully, you heard him say, I'm crossing the event horizon. That means I'm going inside the black hole. And we know that you cannot see into a black hole. Nothing can get out of a black hole. Nothing can go back out of the event horizon. He's now down inside. You look up above, and there is the external universe. He can see out just fine, but somebody on the outside can't see in. That's because of the nature of gravity. Again, images produced through computer simulations with Einstein's equations. But the other interesting thing is that the entire external universe is now inside this ring of hot gas rather than outside. And I'll let you try to figure out how the external universe got inside the ring instead of being outside. Or you can go read about it in my book. Now, as seen from the bulk, the black hole looks like this failed wormhole. But in fact, the singularity down there is much more complicated than what is depicted there. There are in fact three singularities inside the black hole, according to our understanding, working with the laws of physics. The last one was only discovered mathematically using the laws of general relativity, discovered mathematically about 2 years before we started working on this movie. So this is relatively recent knowledge from working with the mathematics of general relativity. There's a chaotic singularity deep down in here. Cooper has fallen into the black hole, and he's trapped between a singularity that is coming in after him and one that's going up from below. The infalling singularity is caused in a really weird way. Everything that will fall into the black hole after him over 1 billion years, because time is so screwed up inside the black hole, it appears to come falling down onto him in a small fraction of a second. And that makes this sort of shockwave type singularity up here. And everything that fell into the black hole in the past, a little bit of it scattered back up and made an outflying singularity, again, that comes flying back up in a fraction of a second. He's caught between these two. These are much more gentle singularities, which he has some hope of surviving, and he does survive, but he survives with the help of a vehicle called the tesseract, which is actually a 4-dimensional cube, a cube with 4 space dimensions. That is a vehicle that's been provided by both beings. These are beings, a higher, more advanced civilization that lives in the bulk, that lives in the 5th dimension. They are called they, a very reverential they, a very reverential tone of voice. Throughout the movie, until one point in the movie, they're called bulk beings. These are beings that live in the 5th dimension. They have made this tesseract, built it, and put it there just to catch Cooper just before he hits this singularity. But after he and TARS, a robot that also falls in here, collected the information about the laws of quantum gravity, and scoops Cooper and TARS up in the tesseract and carries them up into the bulk, into the 5th dimension. So they are getting out of the black hole by going into the 5th dimension, not by going back through the horizon, the surface of the black hole in our 4 dimensions, but up into the 5th dimension. Before I tell you about that, though, let me just explain the tesseract. If you begin with a cube like this, and you go up near the front face and you look in and it's semi-transparent, you see, of course, the top face, the bottom face, the 2 side faces, and here is the back face. And that's what it would look like because of perspective if you go up close to the front face. Similarly then, if you have a 4-dimensional cube, that is a tesseract, then it looks like a central cube surrounded by six distorted cubes. So it's a central cube with 6 distorted cubes around it. Like this is a central square with 4 distorted squares around it. So this is the depiction of the tesseract. Here Cooper is floating in one face of the tesseract, one 3-dimensional face of a 4-dimensional cube. He is carried up into the bulk, into the 5th dimension, by the tesseract. In our universe, the distance back to Earth is 10 billion light years. But because of the weirdness of warped space in the bulk, distance back to Earth up here is only about the same as the distance between the Earth and the Sun, really short compared to 10 billion light years. And so within a few minutes, he's carried up into the 5th dimension, the bulk. He's carried back to Earth within a few minutes. And he then docks, the tesseract docks alongside Murph's bedroom. So Murph is here in one face of the tesseract. Cooper is here in the other face of the tesseract. But Cooper can see Murph above him through light rays that come from the top of Murph's head up through this face and down through Cooper's face. He can see her feet by light rays that come off her feet down through the other faces and back up. He can see her side by light rays that come off of her shoulder here through these other faces of the tesseract to his eyes. So it looks to Cooper like there are 6 Murphs there surrounding him. That's just what it looks like as I've depicted here. And so now we have a movie of Cooper. He is in the tesseract. He's been traveling for a few minutes. He's totally disoriented, totally scared, and you see images of the 6 images of Murph. You're seeing her through the back of her library books, library books. So it's quite a scene, and I was in Norway. I happened to be in Norway with the Prime Minister of Norway, where she was making a public speech. She knew I was in the audience, and she said, you know, Kip, I have never understood how Cooper falls into a black hole and finds his daughter in her bedroom and all her books down inside the black hole. How the hell does that happen? Well, I've just told you, he's not inside the black hole. He got carried up through the bulk and back to Earth. So how do you make sense out of the movie's climax? And I'm coming now near the end of the talk. Christopher Nolan said to me, I think it was in our second meeting, when he was just starting to work on his first draft of the screenplay, 3 drafts he was going to do. He said, I've always admired Stanley Kubrick's movie 2001: A Space Odyssey. And I would like to make a movie whose ending is just as mysterious as 2001 is, maybe even more mysterious. And that's what he did. He then said to me, after the movie was more or less set in stone, he was in the process of editing it. He said, I know you've decided to write a book about the science of Interstellar. You can explain the ending of the movie in your book. And so if you want to truly understand the ending of the movie, the only way you can is by buying a copy. The ending does require some backward time travel, so I want to briefly tell you what we know about going backward in time. What do the laws of physics say about whether we can ever go backward in time? First thing we know is that you cannot move backward against the flow of time. If you and I are here, and I'm moving forward in time, you cannot move backward in time. We are both carried forward like a leaf on a river, on the surface of a river, carried willy-nilly forward in the direction of the flow of time, like in the direction of the flow of the water on a river. But it may be possible to travel out in space, always moving forward in time, carried by the flow of time, like the flow of a river, and yet return before you started. And a beautiful example was devised by my friend Igor Novikov, a Russian astrophysicist, back in the early 1990s. He said, suppose that we have a wormhole with one mouth near a black hole, so time is slowed down at that mouth. The other mouth is up here, far away from the black hole, as seen through the bulk. Time is not slowed down up here. And let's suppose then that we begin with time synchronized through the wormhole, and our clocks are synchronized. But because this clock is moving more slowly down here, it may, after a bit, it may be 1 p.m. here when that clock says 2 p.m. Because the gravity of the black hole, which is pulling hard along that path and causing time to flow more slowly at this mouth. However, that gravity, it turns out, is not pulling through the interior of the wormhole. And so as seen in the interior of the wormhole, gravity is flowing at the same rate up here as down there. And so if all I do is I go out from here, leave here when it's maybe 5 minutes to 2, I travel for about 5 minutes, get down here, so the top clock says 2 p.m., the clock down here now says 1 p.m. And then I just travel up, and the clocks are synchronized through here, so the clock down here says 1 p.m., the clock up there must say 1 p.m. when I get up there. It's a very quick trip. So I started out at 2 p.m., I've gone around here, or I started at 5 to 2, I've gone around here, and I arrive back up there when this clock is back saying 1 p.m., because that clock said 1 p.m. and I've traveled through the wormhole. With the clocks are synchronized to the wormhole, they're not synchronized to the external universe. It's just Einstein's law of time warps applied to a wormhole. It's rather startling. But there's one thing more we know, and that is that all time machines might self-destruct the moment you activate them. Basically, this happens because there's a first moment when you can go backward in time by that technique, as time is flowing at a slower rate down here than up there. And at that first moment, when you go backward in time, light could travel around here, up, come back, and arrive back when it started. So you may begin with one photon of light, and now you have two. They're the same photon, but they're right next, side by side with each other. The two go around, now you have 4, now you have 8. And suddenly you have just one initial photon, you have a crescendo of photons, all sitting up there side by side. It becomes an infinitely strong flux of energy through the wormhole, and it could destroy the wormhole. I know this is a little puzzling. You have to go think about it. But all we have to do, of course, is block things off so the light can't propagate. We just put a wall up there to prevent the light from going through. However, there's something called vacuum fluctuations, or virtual quanta of light, that cannot be blocked out, and they can make this trip and cause an infinite amount of energy to course through the wormhole and perhaps destroy the wormhole just before it becomes a time machine. I discovered this process together with a Korean postdoc of mine back in the early 1990s. And then Stephen Hawking and I had a long debate over a period of several years over whether the time machine is really destroyed or is not really destroyed. And we finally agreed that we don't know for sure. To know what is the fate of that process, we need to know the laws of quantum gravity. So the laws of quantum gravity control the birth of the universe, they control what happens inside a black hole, and they control whether or not time machines self-destruct. Okay, that was a bunch of rather hard physics, but the bottom line is fairly simple. Time machines may well self-destruct, but we won't know for sure until we have these laws of quantum gravity, which Cooper was trying to discover by going inside gargantua. If you want to see the details of what I've been telling you, it's spelled out in more detail than you probably want to. There's a little book not very well known called The Future of Space-Time, which is a set of essays by Stephen Hawking, by me, by Igor Novikov, and a few others. And in there, those essays, you'll find a detailed discussion of these issues of whether or not you can build time machines. Okay, returning back to Interstellar. So we don't know whether or not time travel is possible. Christopher Nolan needed time travel for a reason I'll explain momentarily. But in the movie, and in the movie business, and in all of Christopher Nolan's movies, in areas where you don't really know how nature behaves, he says we have to define a rule set. He calls it a rule set. It's really his choice of what the laws of physics are when you don't know for sure how the laws of physics behave. He says, we will define a rule set for time travel. Three-dimensional objects and fields cannot travel backward in time, but gravitational forces in the fifth dimension can carry messages into our past. And early in the movie, you find Amelia Brand talking about this when they're on the water planet. She says, only gravity can cross dimensions and time. It's also a trick of Christopher Nolan's that in his movies, quite generally, the key to puzzling aspects of the movie sits in the dialogue elsewhere in the movie. That's why if you go to his movie and you're puzzled, you need to go back again and again and find the piece of dialogue elsewhere in the movie that explains what it is that you're puzzled about. Anyway, so the puzzle is in here, and the puzzle involves then gravitational forces going backward in time. And so in fact what happens in the movie, and this is the key to the climax of the movie, is that Cooper sees his daughter with light rays go forward in time through the faces of the Tesseract. But he influences his daughter with gravitational forces that travel through the interior of the Tesseract, through the fifth dimension, backward in time. And the moment in the movie where he is sending those gravitational forces backward in time, you see him pushing on a strip that looks sort of like a board, pushing it back and forth. And that is what's sending these gravitational signals backward in time. I've tried in my own way very quickly to explain the key parts of the climax of the movie. You really have to go see the movie and think about it in order to understand how that all fits together. But he does send back the information that he got from traveling into the Gargantua. His daughter used that information to turn off gravity on the surface of the Earth briefly so that humanity can be saved. You see humanity saved at the end of the movie. That's not quite the end of my story. There was originally a prologue to this movie in which the wormhole was first discovered. It was a prologue written by Chris's brother, Jonah. And in that prologue, the wormhole is discovered by means of gravitational waves from not a colliding black hole and neutron star, but black holes, but instead by something called a neutron star that collides with a black hole. And the gravitational waves travel out through the wormhole down to Earth, and Professor Brand and his team discover these gravitational waves using something called LIGO, a gravitational wave detector. These gravitational waves, then they triangulate on them and discover these gravitational waves are coming from the vicinity of Saturn, and they are being produced by objects that were heavier than the sun, which is impossible. The only way this could be possible is if the gravitational waves are coming through a wormhole, and this is how the wormhole is discovered. And so in the movie, the prologue, you had LIGO, you look at this gravitational wave detector. Now remember, the movie is coming out in 2014, 1 year before LIGO actually discovers gravitational waves. This is a wonderful beginning for the movie. However, that was Jonah's version of the beginning of the movie. When Chris came on board, he looked at that and said, we don't use gravitational waves anywhere else in the movie. Let's get rid of them. Because we want to introduce some additional physics, and we're getting too much physics in. And so I sadly acquiesced, because LIGO is near and dear to my heart. I devoted half a century to LIGO and preparing for LIGO. So I acquiesced, and the gravitational waves and LIGO went out the window. And then was LIGO's discovery, 1.3 billion years ago, in a galaxy far, far away. Two black holes circled around and around each other. This is what they would have looked like to your eyes if you had been there, gravitationally lensing the light from distant stars. They circled around, collided, merged, produced a huge burst of gravitational waves that traveled outward in the galaxy in which the black holes lived, into the great reaches of intergalactic space. For 1.3 billion years, they traveled across intergalactic space. They arrived at the outer edges of our Milky Way galaxy 50,000 years ago, when our ancestors were sharing the Earth with the Neanderthals. They traveled for 50,000 years through our galaxy, and approximately 10 months after Interstellar came out, they arrived at Earth, They hit the Earth first at the tip of the Antarctic Peninsula. They traveled unscathed through the Earth and emerged at one LIGO gravitational wave detector in Livingston, Louisiana. And 7/1000 of a second later, 7 milliseconds later, at the LIGO gravitational wave detector in Hanford, Washington. The LIGO team of 1,000 scientists from around the world analyzed those data for 5 months to be absolutely sure that this signal really was from gravitational waves. And then we announced the result on February 12th, 2016, and it made front page stories in all of the world's major newspapers. 3 days later, Christopher Nolan telephoned me. He said, would you come over to Warner Brothers? He said, I'm in pre-production on my next movie, which was Dunkirk. He said, come on over, I'd like to talk about gravitational waves. I went over, and he spent about an hour talking about how he could have used gravitational waves in Interstellar if he just kept them. How he could have used LIGO in Interstellar if he just kept them. And then he simply stopped. He said, there's no turning back. We did what we did. We have to move forward, and that's it. So where to from here? Well, Stephen Hawking and Linda Obst and I co-authored the treatment for another movie based on real science. This is several years ago, before Stephen sadly passed away. Linda brought on board a studio to make the movie. The studio hired the screenwriter we wanted to hire. The screenwriter has finished a mature draft of the screenplay, and they're negotiating with a potential director for the movie. So if you hang on for about 3 more years, you'll have another one that is totally unrelated to Interstellar. Thank you.
In honor of being here, we would like to present you with a gift. This is a very unique gift, and because you do with such large time, 13 many years, we wanted to give you a small piece of history of our solar system. This is a meteorite. It is 4.6 billion years old.
Wow.
And this is from the Lamar student body, from the Lamar administration faculty, the College of Arts and Sciences, and our department, the Department of Earth and Space Sciences. So we wanted to honor you with this gift.
This is fabulous. Thank you so very much. So I will take questions for a few minutes. The hour is late.